So making these YouTube videos, trying to teach the planet graduate level math, physics and computing theory is my new career. And other than that, I'm totally free. I live off my savings. I live very cheaply because I have American savings when I was a professor in America. And the cost of living in China is about 7 times cheaper than it is in the US. So my American savings go so much further here, and therefore I can retire earlier, and that's what I've done. So I'm free now. I can do utterly what I like. I'm no longer caught up in the treadmill of a traditional role of being a professor, where somewhat cynically I read that the average research paper published by professors is read by one other person, which means, if you think about it, this vast research industry is largely a complete waste of time and money for both people and governments. Because if people are too busy churning out their own papers to read the papers of others, what is the point? Okay? So now I feel that what I'm doing is hugely more significant, right? I have this dream. I would like very much to see high-level education made free for everybody all over the planet. And with the rise of, as I was saying in the introductory videos that I made about 3 months ago now, in those introductory videos I laid out several goals. So free education then is a stepping stone, as I see it, towards the creation, the rise, especially in the third world poor countries, of their middle classes. And with the rise of the middle class always comes democracy. That's, there have been over 100 cases of that over the past 50 years. It's always the middle class that pushes for the creation of multi-party democratic elections in countries. Now, I live in a country which has a brutal dictatorship as a government. It's killed about 80 million of its own citizens, the greatest tyrannical, mass-murdering, brutal dictatorship in history, not just in China, but in history. The only institution I can think that has a worse track record in terms of killing people, and this is even worse than Stalin or Hitler, and that's the cigarette companies. They're estimated to have killed about 100 million people over the past century, in the 20th century. So I would very much like to see the whole planet become democratic, and what I'm doing now is my contribution towards the creation of the rise of the middle classes in many countries. There's still about 80-odd countries that have not yet democratized. So I talk about the concept of de-dictation. In other words, getting rid of the last dictatorships on the planet, including the major one, which is China, which is where I live. Outside China, about 90% of people live in democracies. 90%. So that makes China the big, bad, backward exception. So I'm doing my part to help persuade the Chinese Communist Party that if it wants to survive as a party, because it is doing good things as well. I mean, it's killed 80 million. I mean, it's a horror in that sense. But on the other hand, it's given Chinese the world's highest average economic growth rate for the last 30 years. Right? It's been averaging around 10%. So it would be nice if this diabolical party could convert itself into a democratic party, keep power, but become a democracy, and continue to do the good things that it's been doing. So the best of both worlds. So that's what I'm hoping will happen. And my contribution, as I was saying, is to provide free education. Right? Now, back to the sunlight. Yeah, so I'm an archer. I'm free to do what I like. I go to bed when I like. I get up when I like. You may have heard of experiments that were done by people living in caves. They're totally shut off from sunlight, They were not allowed to have any watches or clocks. So they had no way of telling what the time was. And they would go to bed when they got tired, they would get up when they woke up, and so on. And the researchers noticed that their, if that's the right word, daily cycle lasted about 25 hours. Well, I have no time constraints. I'm arcing, right? So I'm totally free. And my life, in a sense, is almost this bedroom and my books and study and making these videos. And it's dead, it's hot outside, so I tend not to go outside. So it's sort of like my cave, so to speak. So my daily cycle seems to be about 25, 26 hours. So that means day by day, I'm phase shifting, I'm shifting. And now I've shifted enough such that I'm now recording in the daylight again. So you may notice this cycle of the videos tend to have a sort of a light blue tinge when they're taken. Oh, speaking, I should turn on the light. Sorry. Probably change things. Yeah, when it's totally at night, this so-called whiteboard has a bluish tint from the artificial light. And during the day it's sort of whiter. But actually I noticed the best results is when I had both, so daylight and the artificial light. Alright, okay, now to the nitty-gritty. So I'll finish off talking about the position operator, which is fairly simple. So here's your position operator eigenequation. So the usual, the operator, the eigenfunctions, the same, and your eigenvalue. So for position, you can pretty well take any position. So this operator, all it does, it just simply takes the eigenvalue here and multiplies it by the eigenfunctions. It's pretty trivial. You may ask, well, what's the point of creating a position eigenfunction? And I suppose the simple answer would be just to be consistent with the other eigenequations for other observables. Now, there's a bit of a complication in that these eigenvalues here are exact, right? It's a definite position along the x-axis, say x dashed. So these eigenfunctions correspond to an exact eigenvalue. So you then have a bit of a conceptual problem, as I was mentioning towards the end of the previous session, is that these wave functions here, well, they're eigenfunctions, kets, wave functions, and many names for the same thing. They are subject to Born, B-O-R-N, Born's interpretation. Remember, you square the wave function to find the probability of measuring a particle in a given range, and if you integrate over the whole range, that square gives you the probability density. We've talked about that many times now. But there's a bit of a problem here, because if this is zero everywhere except at this exact position x dashed, then this function is zero everywhere and then spikes up infinitely at the position x dashed, and then continues on as zero. So we're talking effectively, this function here needs to be a delta function, right? A direct delta function. So for the rest of this session, I'll be talking about the mathematics, not the physics, the mathematics of delta functions, which is in fact an appendix. It's Appendix C in the text. I'll show you just a minute here. It's just two pages. 2 pages in the text. Appendix C. So I'll just reinforce a little bit what that is. Remember, the Born interpretation says if you take the wave function of some system and you square it, that squared value is the probability density. And to make it a probability, you multiply by the volume, but this probability density depends on x. So to multiply by the whole volume, you have to integrate. Right? Now the particle, let's say talking about one particle, and this probability density is you use to find the probability of finding the particle somewhere in the whole range. So if it's the whole range of the x-axis from minus infinity to infinity, so if you integrate psi squared, the particle has to be somewhere along that axis, right? So that probability has to be 1. Okay? But this is a precise value, eigenvalue. So this wave function here has to give you a precise value for its eigenvalue. So this has to be 0 everywhere except when x is x dashed, takes the value x dashed. So this wave function here has to be 0 everywhere, woo, spikes up furiously and then 0 again. And in the limit, as this becomes precise, with real precision, then the width of that spike becomes infinitely thin, and the height of the spike goes up to infinity, such that this area here remains 1. Now that's the definition. Well, I'll do it a bit more precisely in the appendix. Is the definition of a delta function. So, well, I can give you. I mean, there's many ways you can define a delta function. I'll give you a really simple one that will stick in your memory because it's so easily imagined. So here's your x-axis. Let's say here is the 0 of the x-axis, the origin, and then about the origin, have a very thin rectangle. So just draw a rectangle, and let the height be h, and the width of this rectangle centered with the origin of the x-axis at the center of this rectangle. Let the width of that rectangle be 1 over h. Okay, the height h and the width 1 over h. So obviously the area under the rectangle, of that curve, we call that function, is obviously 1. Okay, and now in the limit, the delta function is defined as the limit of that function as h goes to infinity. Right, so infinitely tall, infinitely thin, and yet the area under that rectangle, under that curve, if you like, is 1. Okay, so that gives you an intuitive idea. Now, in talking here on the appendix, I'll give you a different concrete, manifestation, example of a delta function in terms of exponentials. But there are many ways to represent there are many functions that behave like direct delta functions in the limit. In the limit means infinitely thin, infinitely tall, and area under your curve is 1. Okay, that's the definition of a delta function. Okay, now more formally, you write this Dirac delta function as a delta, and x minus x dashed. Now the x dash is constant. That's just a particular value on the x-axis. Right? It's the x here that's varying. So now it's a function, right? It's just an ordinary function. Well, it's not so ordinary, but just think of it as a function, okay? And it takes 2 values.